Hello, my name is Xiangyu, and I'm from the University of New Hampshire. Today, I'm excited to present our research on EMPC-based tracking control and energy optimal path planning for an autonomous surface vehicle, which I co-authored with Shihab and Professor Singh. As we know, model predictive control, or MPC, is an efficient control method for robotic systems. However, its high computational demand makes it challenging to use on small vehicles like micro ASVs, which have limited onboard processing power and require very quick response times. Furthermore, for these vehicles, optimizing the path for minimal power consumption is crucial for extending mission duration. Our works address the need to balance performance and efficiency. With those challenges in mind, our research had two primary goals. First, to develop an EMPC for waypoint tracking that is both fast and efficient. Second, to analyze different polynomial trajectories to identify the most energy optimal path for the ASV to follow. To develop our controller, we started with a simplified model for the ASV. As you can see on the slide, we decoupled the vehicle's dynamics into two separate linear models, one for surge, which means forward motion, and one for yaw, which means tuning motion. This simplification is key to reducing the complexity for the controller. This slide shows the structure and the formulation of our control problem. The objective is to minimize a cost function, which designed to penalize deviations from the desired path and the amount of control effort used, or respecting to the physical limits of vehicle, such as maximum thrust and turning rate. This slide illustrates the core of our approach. A standard MPC on the left solves that complex optimization problem online at every single time step. This is computationally expensive. Our method EMPC, shown on the right, moves this heavy computation offline. We pre-compute the optimal control action for all possible states and state it in a lookup table. This allows the ASV to find the correct control move almost instantly during a mission, which is perfect for a small vehicle. For the second part of our study, we investigated several different methods for generating the paths between waypoints. We specifically look at four types of polynomial trajectories: cubic, quintic, minimal jerk, and minimal snap. Our goal was to determine which of these smooth paths would require the least amount of energy to follow. To compare the trajectories, we need to model the ASV's power consumption. We made the assumption that energy use is proportional to the applied thrust and tuning moment. Using the equation shown here, we could calculate the total energy required to traverse each of the generated paths. Now for our results. The first plot shows that four types polynomial trajectories generated based on these waypoints is illustrated. On this slide, you can see the performance of the speed and heading control. The plot shows that for every random reference, the controller converges to the desired state very quickly, within just 1.5 seconds, demonstrating its fast response. Additionally, the ASV successfully completes the waypoint tracking mission in the simulator. This slide presents our key finding from the energy analysis. The bar chart compares the total energy consumed for each of the four polynomial trajectories. As you can clearly see, the quintic polynomial trajectory resulted in the lowest overall energy consumption, making it the most efficient option for our ASV. In conclusion, we successfully developed and implemented an EMPC-based controller that provides quick and efficient waypoint tracking for an ASV. Our analysis also showed that among the different paths we tested, the quintic polynomial trajectory is the most energy efficient. This combination of an efficient controller and an optimal path is a significant step to enhancing the operational capability of small ASVs. Our next step is to move from simulation to reality. We plan to conduct experimental testing of this system on our physical ASV. We are fortunate to have access to outstanding testing at the University of New Hampshire, including the Chase Ocean Engineering Lab, which will be crucial for validating our results in real-world conditions. Our research goal is to develop all required technologies to enable a collaborative ecosystem of autonomous vehicle swarms in air, ground, sea, and space. Here is the reference. Thank you for your attention. I would be happy to answer any questions you may have.